Okay. All right. Thanks everybody for joining us. Um, so my name's Paul. I'm the community manager here at DoKC. I'm really excited today. We have Kamya Shethia from the senior software engineer at Etsy, and she's going to be presenting some of her work that she's been doing with Kafka over at Etsy. Before we get too far into that, I would just want to make a few announcements for the community. So yeah, first up, I just want to thank our community sponsors, our particular gold community sponsors, Google Cloud and Percona. You can see a full list of our sponsors at the DOK website at dok.community/sponsors. So yeah, you can check that out. And if you're interested in becoming a sponsor, you can reach out to me. Just a few housekeeping things. So next month, we will not be having a town hall just because we'll be at KubeCon. So hopefully we'll see you there. We'll be there for DOK Day on March 19th in Paris and through the rest of the week. So look out for us there. We can connect and chat. Next, we have an event coming up, which is DOK Day at oh, well, I messed up the we'll be at DOK track at scale. Ignore this title. You can use a QR code to get the link to the event. But that's going to be on Friday, March 15th. So if you can't make it to Paris for KubeCon and you're in the West Coast, you should definitely check out DOK at scale in Pasadena. And that will be on Friday, March 15th, starting at 10 a.m. So check that out. And then I want to announce we have a new local meetup in Tuscany. And this is was organized by Jonathan Battiato. And so if you're in that area, you should definitely check it out. This is the first one. This is one of our newest meetup groups. And also, if you're interested in starting a meetup group, you should definitely reach out to me. We can help organize that for you. Oh, sorry, and that's the link. If you use the QR code there, that's the link to the meetup page. Yeah, and then of course, the big one is DOK Day at KubeCon in Paris. So that's on March 19th. You can still register. Late registration rates are in effect now until March 16th. So don't wait too long to buy tickets if you want to go, because then the price will go up. All right, that is the end of my announcements. So I can hand it over to Kamya. So thank you again. Really glad you could make it and present to us. Oh, actually, one more announcement. If you have questions, you can put them in the chat, and then we'll wait to ask Kamya at the end. So feel free to put those in the chat, and we'll get those questions answered later. Okay, thanks.
Cool. Can you see my screen and hear me?
Yes.
Okay, cool. Thank you all for coming. I'm Kamya. I'm a software engineer at Etsy. And today I'm going to tell you the story of how we ended up improving the speed of our deploys after making our Kafka cluster resilient to a zonal outage. So if you're unfamiliar with Etsy, it's basically an online marketplace for creative goods. There are about 100 million listings on the Etsy marketplace. And those 100 million listings translate to a lot of data that needs to be processed, analyzed, and used in some way. One of those listings is this Harry Potter inspired spoon I once bought for myself. And I found this on Etsy using Etsy search. Kafka is a system that schleps over a lot of the data that feeds into our search models. And Kafka does a lot of other things that Etsy do. My team at Etsy is responsible for the Kafka infrastructure, and we run Kafka on Kubernetes. I'm going to start off by giving you a brief overview on how data is stored in Kafka and how we have our Kafka cluster set up on Kubernetes. To start off with, what is Kafka? It's a distributed streaming platform that is designed to handle real-time data feeds. A Kafka cluster typically consists of multiple Kafka brokers, and a Kafka broker itself is basically a distributed system component that handles a portion of this data. An individual piece of data that is received is called a Kafka message, And these Kafka messages are logically grouped into topics. You can think of a Kafka topic like a table in a database and a message as a row. The data in a topic can then be broken up into partitions. Each partition has an independent chunk of this topic data. And to ensure resilience, each partition of a Kafka topic is replicated across multiple brokers. At Etsy, we have this replication factor set to 3. So to recap, a Kafka topic can have multiple partitions. Each partition contains a unique chunk of data of a Kafka topic. And a topic partition will have 3 replicas, and each of these replicas will be a copy of that data. The diagram on this slide shows how these replicas and partitions are distributed across our brokers. So this diagram shows you 2 topics, topic A and topic B. Topic A has 2 partitions, partition 1 and partition 2 in the kind of yellow-blue color, sea green and yellow color. Each partition has 3 replicas and is distributed across 3 different brokers. Topic B has 1 partition, and that 1 partition also has 3 replicas that are distributed across 3 brokers. So now that we're all Kafka experts, let's talk about our Kafka setup on Kubernetes. Etsy uses Google as our cloud provider, so we leverage Google Kubernetes engine to set up a Kubernetes cluster for us. We deploy Kafka as a Kubernetes stateful set in its own namespace in that cluster. Each of these Kafka brokers are run on a Kubernetes pod. The data for a Kafka broker is backed up by GCP persistent disks. In the previous slide, we spoke about how data for a topic partition is spread across 3 brokers. To tie this back into Kubernetes, this means that data for a single topic partition is spread across 3 GCP pods. Now let's talk about fault tolerance. In the ideal case, a Kafka topic partition will have all 3 replicas available and ready to serve data, which is to say that all 3 Kubernetes pods running the Kafka brokers would be online forever at all times. But that's not actually how things work, right? And Kafka is a distributed system, and it comes with some amount of fault tolerance. We have configured Kafka topics to need at least 2 out of 3 partition replicas to be online and ready to be able to write to a topic. If you think back to the distribution of data across Kafka brokers, it means that we can stand to lose 1 pod without impacting the availability of our cluster. So now let's talk about what happens during a Kafka update. When I say Kafka update, I could be referring to several things. It's just basically any changes we're making to the Kafka brokers. So we could be taking a new version of the open source Kafka framework, which could have like new features or bug fixes. We could be updating a broker configuration parameter, which is basically like something that changes like the default retention settings or compression settings for a cluster. Or we could also be changing something related to the Kubernetes object that we've used to set up our cluster. So remember that our Kafka cluster is able to handle 1 pod being unavailable at a time. And we leverage this to perform live rollouts. Kubernetes has a built-in mechanism for rolling out changes to a stateful set. And it does exactly this. It takes down 1 pod at a time and applies changes to it. And now we're going to talk about that process in great detail. So this process from Kubernetes is called a rolling update. And we're going to talk about how Kubernetes and Kafka behave during this rolling update. During the rolling update, Kubernetes will take down pods in reverse chronological order. So if a stateful set in Kubernetes has 6 pods, the update will go pod 5, then pod 4, then pod 3, then pod 2, pod 1, and then finally pod 0. So assuming we have n+1 Kafka broker pods, Kubernetes will start by sending a SIG-term signal to the broker pod n first. Remember, pods are 0 indexed, which is the n+1 n thing here. Once the pod receives the SIG-term signal, it'll propagate that to the Kafka process. The Kafka process will then shut down cleanly. And once that is complete, Kubernetes will delete the broker pod. Kubernetes will now start a new broker pod n with any changes that we want to make applied to it. After that happens, the Kafka process will start on the new broker pod. Before being ready to receive traffic, the Kafka process will have to recover. Recovery entails rebuilding any indexes it has and catching up on replication lag. Of these two things, catching up on replication lag takes longer, so I'm going to explain that a little bit more. Kafka topic partition has 3 replicas available for resilience, and only 2 out of 3 of them need to be online for the Kafka brokers to continue accepting writes for that topic partition. So when the newly restarted broker comes online, it needs to catch up on all the messages that it missed. And it does so by reading it from the other brokers that hold the other replicas. We do need to wait until replication lag has caught up before continuing on with the upgrade to ensure that at least 2 out of 3 partitions continues to stay available. We use the Kubernetes readiness probe to make sure that this replication lag has caught up. Once broker pod N has recovered, Kubernetes will start taking down the next pod. And this will continue until all our brokers have been updated. Kafka is used for many systems at Etsy. So that means that the brokers have to be fully available during upgrades. So we had to do this one pod at a time. And the process of taking down the brokers, picking down one broker at a time, waiting for it to catch up on replication lag before taking down the next one used to take us about 7 hours. Or to summarize, my day looked like this XKCD meme. The 7-hour rollout was unavoidable for us for a while, until we added zonal resiliency to our Kafka cluster. Let's talk through what it means for our Kafka cluster to be resilient to a zonal outage. To start off with, we moved our brokers across 3 GCP availability zones. We did this by using a Kubernetes feature called pod topology spread constraints. This allows you to distribute pods across 3 GCP availability zones. So if there was a GCP zonal outage, we would have some Kafka brokers available and ready to handle requests. But to ensure Kafka is truly resilient to a zonal failure, we also have to make sure that the data for each topic is available. That means that we needed to distribute the replicas for each topic partition across these availability zones. So if one replica for topic partition in our cluster is on a broker in zone A, we need the next replica to be on a broker in zone C, and the one after that to be on a broker in zone F. In this way, if there's a zonal outage, only one replica for a topic partition will continue to be unavailable, and the other 2 will be online and ready to serve data. This brings us to this kind of cool world where we have a predictable distribution of topic partitions across brokers for the first time. Before multi-zone Kafka, every replica for a topic partition would have been in a broker in zone A. But after multi-zone Kafka, we know that if one replica for a topic partition is on a broker in zone A, the second one will be on a broker in zone C, and the third one will be on a broker in zone F. This makes our cluster resilient to a zonal outage. It also means that all the brokers in a zone could be unavailable, and our cluster would kind of continue to handle requests. And think back to the broker at a time requirement we had for rollouts. With this predictable distribution of topics, we know that taking down multiple broker pods in a zone will not affect topic partition availability. This is great for zonal resilience, but it also provides us with an opportunity to restart multiple brokers at a time whenever we upgrade our Kafka brokers. So we devised a way to do this. And then we called it zone-aware broker upgrades because naming is very hard. So Kubernetes actually natively provides a way to take down multiple pods in a stateful set at once during upgrades. This is called partition rolling updates, and it's kind of a part of the rollout strategy. But the caveat here is that it requires pods to come down sequentially by pod number. And our multi-zone architecture placed every third broker in the same zone. We could have reassigned partitions across brokers to kind of bring it to the distribution that we needed to. But that would have been a very kind of lengthy and manual process. So we opted to just write some custom logic to control these updates. And you might be wondering at this point, why didn't we just design this differently? When we were rolling out changes to make our cluster resilient to a zonal outage, we were focused on the zonal resiliency work. And the opportunity to speed up upgrades came way after. So the first thing we have to do is change the rollout policy for a stateful set. Kubernetes has two ways to control rollouts. The first one is rolling update, and the second one is on delete. The rolling update policy is the one we've been talking about so far. Kubernetes will handle rolling out changes for you. It'll do so one pod at a time. We can configure this rolling update strategy to take down multiple pods at a time using the partitioned update strategy here, but we've kind of already ruled that out. The second policy, which is on delete, kind of gives us more control on which pods we restart and when changes are applied. With the on delete policy, changes will only be applied once a pod is restarted by the user. So we switched the Kafka stateful set to use the on delete policy because we wanted to control how changes were rolled out. Once we did this, we wrote a kind of simple Python script to control the rollout. On the screen, you'll find a diagram that shows you the main loop of our program. The script takes in the number of brokers we want to restart at once. Then the main loop of our program essentially finds some pods in a zone that haven't been updated and deletes them. When a pod in a stateful set is deleted, Kubernetes automatically brings it back up. The script then will wait for the new pods to become ready and then move on to the next batch. It'll do this until all the pods in one zone have been updated before moving on to pods in the next zone, and in the next until all the pods in all the zones have been updated. So we obviously didn't want to have to run something like this from our local machines. So we Dockerized our little Python script and ran it as a Kubernetes batch job. The job is actually triggered from a deploy pipeline on merges to GitHub now. And we added some logic to make sure that we can't deploy multiple versions of the same job because that would just cause all sort of chaos on our cluster. And that's it. We had a new zone-aware rolling upgrade strategy, and it could restart multiple brokers at the same time. So what did this actually do? What was the impact? So to start off with, it improved our rollout speed. We run this script in production with the parallelism of 3, which is to say that we take down 3 brokers at once. For us, this brought down the time it takes to roll out changes from 7 hours in the past to 2 hours now. And you might be thinking, why not speed this up even further and restart all the brokers in a zone at once? And bring this time down even further. When a broker is restarted, it catches up on the data it missed, which is replication lag. And it does so by reading it from the brokers that were not online. This adds additional load to the online brokers, which is acceptable during a zonal outage because that's, this rare event. But it's kind of risky, and doing this during upgrades seemed unsafe. We stopped testing at a parallelism of 3 because we were satisfied with the improvements in speed. And we were very confident that it wasn't affecting any of our broker availability. But it's completely possible that we could push this limit in the future and cut the time down even more. The second impact is fewer client disruptions. So we have numerous client applications that connect to our Kafka cluster. Some of them are managed by our team and some of them are managed by other teams at DoKC. When a Kafka broker is taken down during an upgrade, client applications will temporarily lose connection to Kafka. These applications should generally just, connect to a different broker or the same broker when it's back up and just recover seamlessly. This is the case in theory, but in practice, we've sometimes seen upgrades be disrupted for these client applications, especially when a client application loses connections and has to reconnect to brokers several times, as brokers are taken down and they come back up during an upgrade. The apps tend to get in a weird state, which is easily fixable, but it does require some sort of intervention. Because of this, some teams sometimes prefer to stay vigilant when we roll out changes. So shortening the time period for disruptions was beneficial both to the client applications themselves and for the teams that manage them. And reduce toil. So upgrades are necessary and important. We all understand that. And sometimes they come with a lot of new features that you have to learn about. But for the most part, all the excitement and discovery comes from testing these changes in our dev environment, which is how it should be. And we're very happy about that. But as a result of that, prod upgrades, we consider mostly routine and something that we consider as toil. So my personal favorite way to measure the success of this project has been centered around reducing toil. Did we make our jobs easier or more pleasant in any way? And I think we did. Instead of spending kind of a day just watching graphs and making sure these upgrades are successful, we can now just get these over by lunchtime and do other things. Thank you. That's the end of my talk. If you're interested in learning about this more, this talk is based on two Codex Craft articles that my coworker Andre and I wrote on the Etsy engineering blog, and you can find them on the links on screen. Thank you.
All right, thank you so much, Kamya. That was great. Yeah, if people have any questions, please add them to the chat. And I have a few questions. So you had mentioned fewer client disruptions. Do you have any sort of metrics around that, or even anecdotally, what the difference was?
Yeah, we don't have metrics, but the way the process works for us is we tend to serve a lot of other infrastructure teams. So there are other teams or other platform teams. They're not directly working on client-facing features where the infrastructure platform team, their platform, and then we will work on client teams. So what we typically did was kind of notified them in advance, like a week in advance, and told them, hey, the class is going to be unavailable for a period of time, maybe a day. And now we can say, hey, this is going to be like kind of a half-day affair. And the disruptions themselves were, it's kind of an interesting issue that we have sometimes where sometimes Kafka clients get into this weird state where they don't refresh their metadata fast enough. So they don't receive like fresh broker IPs sometimes, or sometimes when they like keep losing connections, the liveness probes don't kick off on time, and they get into this like back off state. So a simple restart generally fixes it, but you have to kind of restart this app.
Hmm. And what was the impetus for the change in the first place, for doing this strategy?
Yeah. I think I was assigned to perform an upgrade, and I was just sitting there. Well, not sitting there. I was like doing other things. But I was also looking at graphs, and I was like, why are we doing this? Why does this take so long? And I think I had like, it was kind of just like thinking about things while staring at graphs. And I had messaged my coworker Andre at the time, and I was like, hey, I have this idea. Should we do this? And he was kind of on board. So we decided to make this into like a mini project.
Oh, awesome. Okay, I have a question here. Oops, move my desk. From and it's how ephemeral is the data for each topic, and has this increased your cost by 2x based on replicating the data?
Good question. So data and Kafka topics typically have retention settings. Kafka is generally not the final location for this data. It's generally sent to like some sort of more cost efficient storage, like GCS or BigQuery in our case, because we're kind of a Google shop here. So Beta lives in Kafka for like maybe a day, sometimes 5 days, and then it's sent over to an external system. Has this increased your cost by 2 times? So replication in Kafka is kind of a built-in thing, regardless of these upgrades. So we replicate data across 3 brokers, and that's just how Kafka is built. We need to have fault tolerance, and we kind of want to make sure that topics are available when a single pod is down, and that's completely normal in Kubernetes. It's not very frequent, but sometimes pods will go down because like a node will go away or just something weird happens and the pod crashes. So we're kind of prepared for that.
Okay, awesome. Yeah, are there any other tools that you're using to make this perform better? Oops, sorry. make Kafka better for running? Or sorry, I guess I should say, is there anything specific about Kafka that makes it better for running stateful workloads?
Uh, yeah, so Kafka itself backs up its data with persistent disks. So running this as a Kubernetes stateful set basically just makes sure that, if a Kubernetes pod is restarted, we kind of have a backup of this data, and we're not rebuilding or rereading data from like different brokers. So for us, using Kubernetes kind of works out really well. Um, yeah, and I think when we moved to the cloud, we kind of that predates before when I joined the team, and that was kind of a decision that was made. I don't have the history on that, but I kind of just inherited it, and I think it works well.
Okay, awesome. Does anybody else have any other questions they want to ask? Wow, I think we've run out of questions. But yeah, thank you so much, Kami. I really appreciate you taking the time to talk with us. This is really interesting, and yeah, I'm glad to that you can make it.
Thank you.
All right, well, make sure you can watch this like later on YouTube if you wanted to rewatch it. And yeah, hopefully we'll see some of you at KubeCon in March. All right, well, everybody have a nice day, and thank you so much for joining. Bye.